Professor Laurence Harris. So as you well know, Laurence is professor and York Research Chair at York University in the Department of Psychology, and is our longtime former director of the CVR. So I think the rules are that we have to continue to call him director for the rest of his life. It's like being president, right? Laurence, of course, has made many contributions in many areas of perception science. Today he's going to tell us about some of his recent work on the perception of distance and self-motion under the influence of different forms, I guess, of gravity or microgravity. So thank you very much, Laurence, and I'll turn it over to you.
Okay, I think I can just share my screen like that. Okay, that looks good. That's a good thing. Okay, well, thanks very much. That was a nice introduction. I don't think I'm going to be called director for the rest of my life. I'm going to definitely pass those duties on, as Robert knows. So there we go. Okay, so today I'm going to talk to you about the effect of gravity on the perception of distance and self-motion. So there's the Earth. And for those of you who don't know me, I was born over here in Europe on this little island, now isolated in the North Sea. And I came over to Canada, actually a couple of times, but right now, here we are in Toronto. And the point about this is to show you not really where I was born or where I am now, but to point out that we're on the Earth. Everybody's on the Earth, and the Earth is acting as a sort of a reference point for all our perceptions. Here we are standing on the Earth in all different directions, but always vertical relative to the center of the Earth. So this gravity is a very important part of our perceptual experience. Here's some people who are having some trouble with gravity. It's not only very convenient to be sort of held onto the surface of the Earth, but it's also a danger. It really does present a major threat to us. In the course of evolution, it can almost be regarded as a predator. It's something that's going to have had strong shaping abilities onto our evolution. If you couldn't work with gravity and resist its force, then you wouldn't be able to survive. So it's been an important thing. How do we know about it? How do we sense the gravity so that we can actually respond and deal with it? Well, there's two main ways of knowing about it. One is from the pressure points where you're standing on the ground or on the support surface, and you've got tactile information from your feet, in this case, or your bum if you're sitting on a chair, and also from the vestibular system in the inner ear. So I just want to mention briefly about the vestibular system, just so you know what it is. It's a load of canals and a labyrinth structure inside the skull, held inside a protective area inside the skull. And it can be divided into the hearing part, which we're not going to talk about today, the cochlea over here, and also the vestibular system here, which is divided again into canals, which tell you about your rotation, and the otoliths, which tell you about your translation, moving from one place to another. You can actually feel it yourself if you haven't thought about your vestibular system before ever. You can sort of feel behind your ears. There's a swelling in your skull that you can feel called the bulla, and that's actually where the system resides. Pretty much lined up with your eyes, by the way, sort of almost opposite the eyes. Maybe a coincidence. So inside the otoliths, and it's the otoliths that I want to talk about specifically today, or their function, you've got a load of stones, ear stones, otoliths, balanced on hairs. Well, they're not exactly balanced, they're in a gelatinous mass. And when the person moves, then the stones tend to stay where they are by inertia. So the hair cells get bent, and you know about your motion forwards or backwards or up or down. But this system, these otoliths, are also stimulated by gravity. Gravity will also pull the otoliths down in this way and give you a similar signal. So you've got a single acceleration that the vestibular system is telling you about, and your job is to divide it up into which parts are due to your movement and which parts are due to gravity. So we've got a number of solutions to this. The red one is the gravity, and the other one is the self-motion. And there's an infinite number of solutions. I've just illustrated two things that might have been happening to this person, but they would both be providing the same acceleration to the otoliths. So we somehow need to sort of sort out these two things because we want to do different things in response to them. In response to movement, we want to be able to update our position as we move around the world. And in response to gravity, we want to not fall over and to maintain our balance there. So, and our orientation. So we want to do different things to these two components. So we need to separate them. If you're not able to separate them, then you can get these sorts of illusions here. So the person on the left is on a little accelerating trolley thing, and they don't have any vision. They've got their vision is blocked off. So they've got their own acceleration and they've got gravity, and those two combine together to give you this resultant. If you think that the overall response, the overall amount of acceleration is in fact gravity, then you would feel tilted like this. Whereas if you realize that it's made up of these two components, then you'd have the accurate representation. This is called the somatogravic illusion, and you can experience it yourself. When you're in an aeroplane about to take off, zooming along the runway, accelerating along the runway, you'll often feel a sense of tilt before the plane itself actually does tilt to go off into the, to take off. So how can we do this? How can we perform this distinction to get the two components? Well, one thing is that gravity is a constant force all the time. So we can assume that things that change quickly are due to U, and things that don't change quickly are due to gravity. And this may be one of the ways that the brain does solve the issue. Also, the canals can tell you about head rotation and update the idea of where gravity actually is. So we've got a representation of gravity inside our heads, and then when we tilt our heads or change our orientation relative to gravity, that change will be picked up by the canals, and you can use that to say, well, this is where gravity is, and so everything else is due to my own movements. An easier way to do it is by just using other senses, so that vision can tell you what your movement is and what your orientation is. And so by combining vision and vestibular information, you can solve this problem. And normally this is available to us. You can just open your eyes and tell the difference between whether you're moving or not moving. So what I'm going to look at today is some of the consequences of this visual vestibular interaction that is always present. Okay, so that was the sort of introduction. Now, what we're going to look at now is the effect of gravity on the perception of distance. What happens when the direction of gravity is not where you expect it to be, when we actually introduce one of these visual vestibular conflicts where the two things are telling us different ideas. Well, if we want to measure perceived distance, the first thing is how you're going to do that. And so what we use is we exploit the fact that in order to understand how big something is, you need to know how far away it is. So if you make an error about judging its size, then that can be explained by making an error in judging its distance. So if we've got an object at a particular distance here, and it moves closer to us, then it makes a bigger angle. So by looking at the angle that it's making, we can judge where they think the object is, how far away it is. And in order to do this, they have to make a judgment about the size of the object relative to a reference length that they hold in their hands. So they get a reference length, which is a certain distance, certain length, and then they simply adjust the target until it appears to be the same length as the reference. And then we can see if they've made a mistake. If they've got it too big, then it tells us they think it's too close. If they make it too small, then it's because they think it's further away. So here's the person, we give them the rod, we give them a reference stick over here, and we want to put them in a nice environment where they've got lots of cues to where upright is. So we put some things in the room like that. And now we want to alter the relationship between that person and their visual cues to alter the relationship between the gravity cues and the non-gravity cues, the visual cues. So we can do that by rotating the person around like this inside the room. And now their own body is telling them that up is towards the top of their head, but vision is telling them that it's in the old direction. Or we can tilt the room. In this case, we've done the same manipulation relative to the body. Everything else is the same as it was in the previous one, but now gravity is in its normal position in the going through the top of the head. Okay, what happens when we do that is we do get distortions of the perceived size and therefore the perceived distance of the target. So the first column here is just when everything's normal, they're sitting upright and everything. But when we rotate the person, so they're lying on their backs inside the room, then we get a reduction in the perceived distance. Things appear closer. They need to be made bigger to match the reference stick. What's interesting is that when the observer only thinks they're tilted, so the gravity and their body is all the same, but only the visual world has rotated around, which gives them the impression that they have been tilted, then the same phenomenon is found, that they think that they are tilted and the objects appear closer to them. So why might that be? Why might it be that, that when they're lying on their backs, or they think they're lying on their backs, but things appear closer? Well, gravity is an acceleration. And so here's this person just sitting there with gravity. Obviously, everything's aligned here while they're sitting upright. And the reason I put the arrow upwards is because we can regard the acceleration of gravity as being an upwards acceleration. To illustrate this, imagine yourself in a box floating around in the universe. And what do I have to do to that box to make it to provide pseudo-gravity, to simulate gravity? Well, what I have to do is I have to take the box and I have to pull it upwards so that you're thrust to the bottom of the box and would feel normal gravity if I maintained that acceleration at 9.8 meters per second squared forever. So that's why I'm putting it as an upwards arrow. Okay, but when you lie down now, you've got sort of two potential ups. You've got the direction of your head and any visual cues that are telling you that, and you've also got the acceleration of gravity here. So if you're thinking that you're upright and that you're taking this one as your actual cue to being upright, then what are you going to do with gravity? Well, perhaps you regard it, at least partially, as indicating some kind of movement. So you're sort of moving in the direction of gravity towards the object, or maybe just a tendency to move in that direction, which would normally make you closer, of course, to the object. Well, if this line of logic is true, then when we put the person the other way around, then they would still have this sensation of movement, but now, of course, we'd expect the opposite. So things would appear to get smaller, further away. All right, well, let's try that. So we've taken a person and we've arranged them upright or lying on their backs or lying on their fronts with the idea that we'd expect opposite responses or opposite results for those two orientations. You can see he's holding the reference rod in his hand, so he's got that reference there. And what happens, oh no, also it's a virtual reality system. You see they're using virtual reality now rather than an actual room, but we're using virtual reality system. And in the virtual reality, they're seeing a scene like this, which is always upright relative to them. So however they lie or they move around, the sky is always above their head and the ground is always towards their feet. And they have a target object here, and that's going to change its size depending on what how they judge the size of that object relative to the reference point they've got in their hand. And this is what happens now. So we've got upright here and prone on their backs and supine on their tummies here. And so now what we've got, those are labeled the wrong way around, but it doesn't matter because the thing goes in the same direction in both cases. So this is the correct answer here. And in both cases, they need to have the rod a little bit longer in order to match the stimulus, a little bit longer in order to match the rod, which corresponds to them being closer. Now notice that even when they're upright, we tend to get a tendency to have things a little bit closer. And this is probably a result of being in virtual reality. But the point we want to look at here is the relative changes when they're prone and when they're supine here. And you'll see that these are both significantly different and they're both in the same direction. The object needs to be made larger when they're lying in either direction relative to gravity. So the acceleration theory, the idea that there may be a movement or a tendency to move, is not correct. Maybe it's any conflict between gravity and perceived upright that has this effect. It's not a directional thing, but simply a detection of conflict. So let's go for the ultimate conflict and take people up into space and see what happens there. So this diagram here is just to illustrate to you what's going on in the International Space Station. It's important to know that the International Space Station does not orbit very high above the Earth. It's about 400 kilometers away, about a little bit less than the distance to Montreal. So it's really not that far away. It's not very much further from the center of the Earth than we are. So it's going to still be subject to 98% of the gravity that we're experiencing now. What's happening though, so if you imagine a person, a very big person, standing on the Earth and throwing a ball. If they throw the ball too fast, it's going to go off into space. And if they throw it too gently, then it's going to fall down to Earth. But if they throw it just right, it will actually continue its pathway all the way around the Earth. It'll be in free fall all the way around the Earth. And that's how we're generating zero G in the space station. You can use the same principle yourself, sitting at home, or not sitting at home, but standing at home, by simply jumping in the air. Just jump in the air, kapow, like that. Then as you come down, you're in free fall and you're in microgravity. You've cancelled out gravity. There's no gravity there at that point, no effective gravity. And that's the principle that's being used here in the space station. So we can get them to work with virtual reality again. Here's one of our astronauts putting on the equipment, holding the reference rod, and doing that same experiment in space. Now, I want to point out that these experiments are actually not complete yet. We're going to do 12 astronauts altogether. And so far, we've done the ones that you can see on the diagram here, blocked in. So we don't have a complete data set yet, but it's getting there. We've got quite a lot of people. We're going to fill in those last few blanks over the next couple of years. In fact, we're filling in that blank there on Tuesday. So we're still collecting data, but we're just going to tell you about the data we've collected so far. What we're doing is we're testing them before they go up, when they very first arrive in orbit or within the first few days, and then 100 days later, after they've had a chance to adapt to the zero-G environment, then as soon as we can after they come down, and then sometime later to see if there's any recovery there. So that's what I'm showing on this graph. We've got, on the left-hand side, we've got the astronauts, and on the right-hand side, we've got control subjects. And for the astronauts, here's before they go up, in space immediately, in space after they've been there 100 days, when they come back, and when they've come back for some time. And we also have our control subjects who are tested at the same intervals, the same project, the same experiment, to see if there's any changes that are just due to being tested multiple times or something like that. Now, when we look at the data here, the vertical axis is the perceived object size. So as it goes up the axis, objects appear to be closer. And what we see is when they first go into space, we get an effect. The objects appear closer when you first arrive in space, and that perception of being too close is maintained all the time that they're in space, and interestingly, does not recover when they come back. They're still having a perception of everything being a little bit closer, even when they've been back on Earth for a couple of months. The control subjects show no effect on average throughout the whole procedure. Okay, so when gravity is not where it's supposed to be, doesn't line up with the visual cues, there's a sensory conflict, and this conflict affects the perception of space and makes things appear closer. Well, we don't really know exactly why it would be closer, and anybody who's got any good ideas for the direction of the thing, I'd be very happy to hear. But I think it does have some ecological validity. If you're in a conflicted situation, if you're lying down so that gravity is not aligned with the body or anything, then this is the time when you think things are closer and where you're more vulnerable. So perhaps being more vulnerable and seeing the tiger as being even closer than it actually is gives you an advantage in being able to deal with that sort of threat situation. All right, so now, second part, or the third part, the effect of gravity on the perception of self-motion. Is there a similar effect of visual vestibular conflict on the perception of self-motion? And I say through space, I just mean moving around on the surface of the Earth, at least initially. It's important to realize that vision can generate a sense of motion on its own. Just looking through the car window here as you're driving along, you get a lot of information and a lot of sensation of motion from the visual flow there. You see the blur on the image on the right, and the motion on the image on the left shows you the sort of motion that you're making. So you can tell from this optic flow that the person is heading in this direction. This is where the car's going. And all the other information can tell you a little bit about the speed and the distance that you're traveling. So we wanted to look at this in situations where we have a clear clues to orientation, so that we can alter the orientation relative to gravity and set up one of these conflicts. So here we have a hallway with a target at a certain distance away. Here's shown on the left is the target. Then the target disappears and the hallway appears, and now you get optic flow, and you simply have to press a button when you get to the target. Then we repeat that same idea using a star field environment, which does not give you the visual cues to orientation, and therefore does not give you a conflict when you're changing your orientation. So this is what it looks like. Here's the hallway. Zooming along, you get a target at some distance, and then you push the button when you think you've reached the target about there, something like that, see? Okay, and the same thing for the non-oriented hallway, moving through there without any obvious sense of where up is, and you get a target floating around in space somewhere, and you simply press the button when you think you reach the target. So now we repeat those experiments with the person supine and prone, and these are the results that we get here. So what you'll see, this is the gain plotted relative to when standing. So when I say gain, that's the amount of optic flow that you need to move through a certain distance. If you have a very high gain, then it means you need less motion. You'll press the button really soon because you're using up all that visual information and you think you've gone a long distance, and you'll press the button really quickly. On the other hand, if you have a low gain, it means you need a lot of visual motion to be able to go through that distance. And so these are plotted relative to when they're upright. And what you see is that when they're supine or prone, in the hallway environment, then the gain is larger. That is, they need less motion than when they were upright. Now we repeated it, not having the whole body upright or supine or prone, but instead having the head tilted up or tilted down, trying to simulate the supine and the prone posture without actually having the body prone. So we're really just altering the vestibular signals, but not the body signals, to see if that makes any difference. And what you see is when they're prone, when they're looking down here, like in this picture here, and they're looking downwards, then the gain is indeed higher. They need less motion than when upright, but not so when they're looking up in this direction. So now we repeated the experiment in the hallway using a different group of people in the star field here. So these last two are the star field, and they're not significantly different from standing when they're standing. So there's no obvious difference there. But what we noticed as part of that experiment, we repeated the first one. So we wanted to have these new subjects, but we wanted to have them in both the hallway and in the star field. So those two are this is the hallway, this is the star field. And what you'll notice is that the two experiments produce rather different data. Although in the prone orientation, the responses were significantly different from upright, in the supine, there was a bit of flexibility, a bit of variation between the people. So we wanted to know what was causing this, and so we asked them some questions. We asked them basically, what did you experience when you were in the situation, when you're wearing this virtual reality system and you're lying down? What does it feel like to you? Does it feel like you're standing up, corresponding to the orientation given by the visual cues, or does it feel like you're lying down and looking at a tilted picture, tilted display? So they've got two potential answers there. And what we found is that people divided up into two groups. Some of them felt that they were actually upright, that they were able to ignore gravity, and they felt that this was upright and that they were floating around or be standing in a upright room. And other people felt well, they were not fooled. They understood what was going on. I'm lying down on my back and I'm looking at a virtual reality world. So we've got two groups of people, those that are subject to what we're calling visual reorientations and those that are not. So the visual reorientation illusion is something in where the vision signal somehow dominates and causes you to change your orientation. It's most pronounced perhaps in space. Here are some astronauts floating around in the International Space Station, and you know which one is the upright astronaut? There's no answer there. So each person is going to have their own upright, and they can sometimes flip between one and the other and have a different orientation that they regard as their own personal upright. More extreme example is this person on the end of the Canada arm, and you know there's really no obvious cues to upright there at all, and that is why it becomes very disorienting. Sometimes they'll use the station that they can see in front of them as being the reference point, and that would represent their bottom, their way down. And sometimes they catch a glimpse of the earth beneath them, and then they feel that that's down, and so it can be very disorienting. And they're flipping between different orientations that are regarded as upright. So we can take those same data we've just talked about and plot them instead in terms of the likelihood of experiencing a visual reorientation illusion. And now it sort of makes much more sense that if you've got a higher chance of experiencing a VRI, then this corresponds to you having a higher gain in your self-motion thing. And that might explain what happens here. These two graphs, these two bars here, corresponded to the person tilting their head up or down. And when they're tilting their head downwards, it's not. It tends not to produce so much of a virtual reality, a VRI illusion, but tilting upwards does. Probably because this is this is a much more unnatural situation to be tilting your head upwards, and so maybe you don't actually experience that as being the actual situation that you're in. So you have less of a VRI when you're trying to do this. Whereas when you're looking downwards, that's a much more natural movement to make, and something that you seem to be able to incorporate and produce more of a feel that you're standing upright, even though your head is tilted. So that's why these two appear to be different. They correspond to the two appropriate points on that graph. So the amount of gain increase depends on how likely they were to get a VRI. And the VRI corresponds to the largest conflict, because there you're taking physical gravity and just like ignoring it. So you're just shutting that part down. You're in the biggest environment, the biggest conflict situation. So we conclude again that it's conflict between the visual and non-visual cues to gravity that are causing these perceptual effects. In the case of the VRI, the maximum conflict, and therefore the visual cues are the most evocative. So, okay, if it's going to be conflict again, let's go into space. Here's a person moving around in space. This is David Shonjak, our Canadian astronaut. And you see they move in a way that, of course, is very different from on Earth. They're basically gliding around like Superman. So we gave these astronauts this test as well to see what their perception of distance, of motion distance was. So here's the task that we gave them, very similar to the one I just described to you with the hallway. And they get a target down a corridor, and then corridor will move past them, gives them this illusion or the sensation of self-motion, and they push a button when they think they get to the target. And there's another target there, and now they have the same movement and push the button when they think they get there. So we can estimate how much optic flow they need to produce the illusion of moving through a given distance. Just a reminder that this is not a finished project yet. We've still got lots more of the yellow areas to fill in, but we have got quite a lot of green areas that I'm telling you about now. So same format as before. On the horizontal axis, we've got the different times that they were working. Before they went up, space 1, space 2, after 100 days, when they came down and again, and the control study across here. And what we see in this data set, this doesn't work, or it doesn't happen. We don't get a change in the gain of the self-motion perception when they first go into space. There's no significant change. But what does happen is that after they've been in space for 100 days, their gain actually goes down. That is, they need more optic flow than they needed when they were on Earth. This is the opposite direction to what it was before. You remember that when we first went into space in terms of distance, they got closer, but now we're getting the opposite effect here. Okay, so some effects of gravity on perception. When lying prone or supine on Earth, you need less visual motion to feel that you've traveled through a given distance than when you're upright. And as we showed in part 2, objects appear closer when you've got this conflict. The more VRI you experience, the less motion that you need. And so it's not just the effect of gravity, it's the effect of where you think gravity is that determines whether there's a visual vestibular conflict, which then leads to these effects. So why was there no immediate effect of going into space on self-motion perception? That's supposed to be a conflict, at least it was in terms of our sense of orientation. As soon as you go into space, your sense of orientation is now obviously very much distorted. It's become just your own personal interpretation of where orientation is. And so you have a constant conflict between whatever that is and the fact that there's no gravity that supports that decision. But in space, because there's no effective gravity, the otoliths are always telling you only about self-motion. See, the otoliths now are sort of released. They're not being held down by gravity at all. And so if ever they're active, it always indicates self-motion. So in fact, when we're talking about self-motion, there's not really a conflict, and therefore no change in gain. So the decreased gain that's found after 100 days in space may be to do with an adaptation to flying around like Superman all the time. You know that you saw the video of him gliding around there, and the decreased gain means that you would tend to overshoot. That means that you're pushing the button too late, not too early. Now you're going past the subject, the target, and pushing it too late. And this may be a sensible adaptation to the rather strange environment that they find themselves in, which is that it's very important that they reach their target. As you saw, he's drifting along through space, but in the middle of that drift, he's not touching anything. He's got to give himself a push at the beginning, or she, you know, the astronaut has to give himself a push at the beginning and hope that it gets them all the way to the next target. If they undershoot, if the gain is too large, then they risk getting stuck in space. Here's an astronaut who's got stuck. He's just in the middle there, and he can't get out. Right? He's trapped there because there's nothing that he can push against or that he can reach, and so he's not able to move around and would have to call on another crew member to be able to push him away from this static point. This apparently has happened to Chris Hadfield while he was up in space, or at least he realized that it was there. And so this strategy of lowering the gain for visual motion may be a strategy that makes it easier to move around in space and avoid these embarrassing situations that you see there. So here's Christina Koch coming back to Earth after she's been up there as one of our subjects. She actually had the longest stay in space by a woman as of February the 6th, 2020. She was up there for 328 days, which does sort of exaggerate or point out how long it takes to do these experiments. We have to, it takes a long time to turn over the astronauts and therefore to turn over our subjects. So thanks for listening. This is the team of people that were basically involved in doing all the work. Niels Barry, Michael Jenkin, Megan McManus, Sean Georges, Rob Addison, and John Kim. And to all the rest of the team, and of course our sponsors, the Canadian Space Agency. Thank you.
Wow.